तो ये जो आप इसको you have to see कि what are those factors जिसकी वजह से इसकी एफिशिएंसी कम होती है। तो इसका मतलब कि जो हम करंट मेजर कर रहे हैं, बिस्मिल्लाहिर्रहमानिर्रहीम, अस्सलाम वालेकुम बच्चों, वेलकम टू द नेक्स्ट एक्सपेरिमेंट in modern physics laboratory. Today we are going to prove the inverse scale of a radiation source. बड़ा simple सा experiment है जिसमें हमने prove करना है कि the power received at any distance d is directly proportional to the 1 over d square or r square, where d is the distance between light source and the detector. ओके, एक्सपेरिमेंट में क्या है, हमारे पास एक लाइट सोर्स है जिसको कि हम ऑन करेंगे। इट्स 100 वाट टंगस्टन हैलोजन लैम्प, और हमारे पास एक फोटो सेल है जो विच इज़ अ पीस ऑफ अ सोलर सेल जिसकी डायमेंशंस 3 सेंटीमीटर बाय 1 सेंटीमीटर है। ये आपको ज़रूरत पड़ेगी इन योर कैलकुलेशंस। इसी तरह आपको ये 100 वाट द पावर ऑफ द लाइट सोर्स, इसकी भी ज़रूरत पड़ेगी क्योंकि इसका ताल्लुक डायरेक्टली इसके स्पेक्ट्रम के साथ है। Now in experiment what we do is we switch on the lamp, and after some time we start changing the distance between the lamp and the photocell, and we measure the current which is flowing through this solar cell. So एक एमीटर लगा हुआ है यहाँ पे जिसमें हमें करंट हम मेजर कर रहे हैं। तो जब हम एक्सपेरिमेंट फिजिकली दिखाएंगे you will see all these parts over there, उसमें और ये एक टेबल बनाएंगे and then you will go through it. Now let's go to the theory of why we want to do this experiment. I'm not going to do all the mathematics. Handouts में you already have this mathematics, and in your modern physics course you have done work in that one regarding the theory of this experiment. So we start with the Stephan-Boltzmann empirical law, which gives the power radiated by any source is equal to the sigma T4, where sigma is a constant or T is the temperature of the body, ये जो radiation emit कर रही है. Now what we need to do is, and this is total power is measured by in watts per meter square. हमने क्या करना है? Okay, so we need to measure the this power at any distance d. यहाँ पे कि कितनी पावर पहुँच रही है. Okay, so very simple mathematics. We measure the power at the source and equate it to the power at the distance r using simple mathematics. What is the surface area of the source? Multiply it with the power radiated by this one. So that's the total power radiated by the body. And then at any distance r, we take another sphere. So this is the surface of area of this sphere, जो कि which actually, so I can and multiply it with the power received at this distance r. So it's like this. We have this source which is at temperature T, and then its radius is r, and we have another sphere at a distance r. Okay, so we can measure how much power which is being dispersed or transferred at this sphere using this equation. So you can see power received at distance r is given by r square over capital R square, which is the radius of the radiating body, divided by r square, where r is the radius of r is the distance where we are measuring the power, and we multiply it with the total power, which is given by the Stephan-Boltzmann law, sigma d4. So we put it over here, and we can see that we can write this, the power received at point r is equal to some constant multiplied by 1 over r square. So if I look at that one, so the power received at point r is proportional to 1 over r square. ये हमने प्रूव करना है इस एक्सपेरिमेंट में. So this will give you a straight line. अब यहाँ पे ना very interesting. Once we have this straight line, we can equate this one to the slope. So this is slope of the straight line. So r square is the radius of the source, sigma is a constant, T is the temperature. टेम्परेचर आप इधर से भी निकाल सकते हैं फ्रॉम हेयर. सो दिस इज द इलेक्ट्रिकल पावर. एज्यूमिंग द 100% इलेक्ट्रिक पावर इज कन्वर्टेड इनटू द रेडिएशन, so you can measure what the temperature is. But it does not happen. Some of the electrical power is lost in resistance. So resistive heating होती है, some other phenomena होते हैं. So you can assume easily 70 to 80%, or maybe RMS value से आपको अंदाज़ा हो सकता है. You take inverse of RMS से भी आप अंदाज़ा कर सकते हैं कि कितनी electrical power जो है converted into optical power. From there you can find out the temperature of the this lamp. That's one way. The other one is you have the slope here. इस slope को equate करें इसके equal and see what temperature you get over here. So this is R is the radius of this lamp. तो इस filament का आप देख लें कितना radius dimensions क्या हैं. Put it over here. Sigma is a constant and find out temperature. You'll find कि ये नंबर हो सकता है इसके बिल्कुल बराबर ना आए, बहुत ज़्यादा दूर हों. Why? So I've written a question over here where you have to think about that. We are using a photocell. What is the efficiency of photocell to convert a photon into electrons? Photoelectric effect जो सा हो रहा है या इसमें photoelectrons produce हो रहे हैं. In slides and handouts you are given how a photocell works, semiconductor photocell works. तो उसमें आप देख, उसमें स्लाइड्स में उसकी एफिशिएंसी भी गिवन है कि फोटोसेल की एफिशिएंसी कितनी होती है. सो यू हैव टू थिंक अबाउट नंबर वन, व्हाट इज़ द एरिया जो कि इस स्फीयर का है, दैट इज़ द फ्रैक्शन ऑफ द पावर विच इट इज़ रिसीविंग फ्रॉम दिस सोर्स. नंबर टू, व्हाट इज़ द कन्वर्जन एफिशिएंसी. जिस तरह इसकी कन्वर्जन एफिशिएंसी है फ्रॉम इलेक्ट्रिकल टू ऑप्टिकल, वी हैव टू सी. इसी तरह ऑप्टिकल टू इलेक्ट्रिकल कन्वर्जन है. Photocells never work at 100% or even at 50%. Maximum commercially available work around 25-26%. तो ये जो आप इसको you have to see कि what are those factors जिसकी वजह से इसकी efficiency कम होती है. तो इसका मतलब कि जो हम current measure कर रहे हैं is not exactly the same power. It is the fraction of the power which is being converted from optical to electrical. You have to find out this answer in this one. Okay, now ये इसका एक part है. The next part is we can use the Planck's radiation law in order to determine this temperature of the radiating body. तो Planck's radiation law से हम Wien's displacement law drive करते हैं, और Wien's displacement law also gives us the temperature of the radiating body. So let's look at that one.